Hi, welcome to iEducator. This is Teacher Jeff. I'm an educator and an engineer by profession. And today we will discuss Chapter 11. And Chapter 11 is all about hearing, sound, noise, and vibration. And in today's lesson, there are 5 key areas that I'm going to be highlighting today. First, we have the introduction. Second, we have the different terminologies. Third, we have the measurement of sound. Fourth, we have the human ear protection. And finally, we have the design of the acoustic environment. And at this point, let me discuss to you the introduction part of our lesson. Now here, if we see acoustic waves, it can be defined as pressure or pressure fluctuations in an elastic medium. On the other hand, if we say sound, it is the auditory sensation produced by these oscillations. Now, in air, sound consists of oscillations about the ambient atmospheric pressure, as shown in figure 11.1. Now, as you can see in figure 11.1, vibrating surfaces or turbulent fluid flow can act as the source, propagating alternately highland low pressure areas. The amplitude of the acoustic wave is expressed in newtons per square meter or in pascals. 1 pascal is equivalent to 1 newton per square meter. The threshold of hearing or lowest amplitude of pressure oscillations in air detectable by the ear is equivalent to 0.0002 Newton per square meter at a frequency of 1000 Hertz. Now, on the next key area, we have the terminologies. So here, we will be discussing the different terminologies if we speak about hearing or sound. Now remember, frequency and amplitude define a pure tone. Their subjective counterparts are pitch and loudness. The perception of pitch also depends on the waveform, and that of loudness depends on frequency. A healthy young person can hear sounds in the range of 16 to 20,000 Hertz. Now, if we say noise, it is usually defined as a sound or sounds at such amplitude as to cause annoyance or interfere with communication. And if we say sound, it can be measured objectively. Noise is a subjective phenomenon. On the other hand, if we say amplitude of sound, it is evaluated by measuring the sound pressure level or the SPL. Here, the range of SPLs to which the human ear is sensitive is so wide. That would be 0.0002 to 20 newtons per square meter. That linear scaling would present a problem. And for this reason, a logarithmic scale or the decibel scale is used. And finally, if we say decibel, it is a dimensionless unit related to the logarithm of the ratio of the measured sound pressure level to a reference level, usually taken to be the threshold of hearing. Now, the smallest noticeable difference in intensity between two sounds is about 1 decibel. Now, commercially, sound level meters measure and display an RMS or the root mean square, SPL or LP, where LP is equal to 20 log sub 10 multiplied to the quantity of P over P sub R decibel, where L sub P refers to sound pressure level in decibel, P refers to sound pressure in newtons per square meter, and P sub R refers to the reference sound pressure level, which is equivalent to 0.00002 Newton per square meter. Now, in order for us to better understand this, let us have an example. So, for example, if the RMS SPL is 2 newtons per square meter, then so all we need to do is to plug in the value to our formula. So that would be log sub 10 times 2 all over 0.0002. So therefore, our log sub 10 is equal to 5, and L sub B is equal to 100 decibel. Now, on the next key subtopic, we will be discussing the human ear. And the function of our human ear, it actually converts sound waves in air into nerve impulses, which travel along the auditory nerve to the brain. Now, further processing in the brain results in the perception of sound and the recognition of auditory patterns. A simplified diagram of the ear is presented in figure 11.2. Now, as you can see in figure 11.2, it shows the composition of the ear. As you can see, it consists of the outer ear, which is indicated as letter A in the figure, the middle ear, which is indicated as letter B in the figure, the inner ear consisting of the cochlea, which is indicated as letter C in the figure, the semicircular canal, which is indicated as letter D in the figure, and finally, the eustachian tube, which is indicated as letter E in the figure. Now, hearing requires 3 main steps, and in each, energy is converted from one form to another. First, pressure variations due to longitudinal waves in the environment are guided into the external auditory meatus, where they cause a mechanical vibration of the tympanic membrane or the eardrum. Here, the tympanic membrane or the eardrum is actually connected to 3 small bones or ossicles in the middle ear, which in turn are caused to vibrate. Second, mechanical vibration of the auditory ossicles is converted to wave motion in the cochlear fluid at the oval window. And finally, wave motion in the cochlear fluid is converted to nerve impulses in the auditory nerve by hair cells in the cochlea. And anatomically speaking, the ear is divided into 3 parts at which these energy transformation take place. First, we have the outer ear, and the outer ear consists of the ear flap or pinna, the external auditory canal, and the eardrum. Now here, the pinna is like an ear trumpet that funnels sound into the canal. The pinna is relatively small and unimportant. When one is attempting to listen to a faint sound, it is actually best supplemented with a cupped hand. Sound waves travel to the eardrum, right? And the sound causes the membrane to vibrate, and these vibrations are transmitted to the middle ear. And the middle ear is an air-filled bony chamber connected to the outside atmosphere by the eustachian tube, which terminates at the back of the throat. Now here, discrepancies in air pressure on either side of the eardrum are potentially harmful. In fact, swallowing momentarily connects the middle ear to the atmosphere, enabling pressure differences to be equalized. And so for that matter, the popping sensation of the ears experienced when changing altitude is caused by this sudden equalization of pressure. And finally, the inner ear is known as the cochlea. It can be modeled as a fluid-filled tube separated into an upper and lower half by a membrane. Now, as you can see, this is a clearer picture of the human ear. And as you can notice, this is divided into 3 parts. We have the outer ear, the middle ear, and the inner ear. And as shown in figure 11.3, this is a simplified view of the cochlea and wound to reveal its tabular structure. And moving on, we have the middle ear. And here, vibrations of the eardrum are transmitted to the inner ear via three connected bones, which comprise the acicula system. And second, the malleus is connected to the center of the tympanic membrane at one end and to the incus at the other end. Here, movements of the eardrum cause movements of the malleus that are directly transferred to the incus. Third, the opposite end of the incus is connected to the third auditory ossicle, which is the stapes. And finally, the far end of the stapes is known as the face plate. It lies against the opening of the inner ear, which is the oval window. So the auditory ossicles are supported by ligaments, and the tensor tympani muscle keeps the tympanic membrane under tension, like the diaphragm of a microphone. Movements of the tympanic membrane are transmitted from the auditory ossicles to the oval window of the inner ear. Now, the ossicles play an important role in increasing the efficiency with which sound is transmitted to the sensitive hair cells of the inner ear. Since the inner ear is filled with fluid, sound energy has to be transmitted from air to fluid, and the transmission loss from air to water is about 99%, which is why fishermen can listen to the radio while fishing without frightening the fish away. So what is then the function of the auditory ossicles then? Well, the function of the auditory ossicles is to transmit sound energy from air to water. Now, as you can see on the presented pictures, the first picture shows us a picture of the human ear. And as you can notice, encircled with red, that refers to the auditory ossicles. Or the auditory ossicles, rather, they actually act as a lever system in which displacements of the malleus at the tympanic membrane cause corresponding but reduced displacements of the faceplate of the stapes. Now, this reduction in amplitude is accompanied by a corresponding increase in force of approximately 1.3. Now, the surface area of or at the faceplate is approximately 17 times smaller than that at the tympanic membrane, and therefore, the pressure of the air against the tympanic membrane is increased approximately 22-fold at the stapes against the oval window. And without the auditory ossicles, the threshold of hearing would rise by about 30 decibel. Now, volume control is achieved by the tensor tympani and stapedius muscles. Intense sounds, particularly at frequencies less than 1,000 hertz, causes these muscles to contract to pull the malleus and stapes away from the inner faces of the outer and inner ear. Now, this attenuates loud noise and protects the inner ear from damage. Differences in the effectiveness of this attenuation reflex may help to explain why some individuals are more susceptible to noise-induced hearing loss than others. And like I said earlier, anatomically, the ear is divided into three parts. We have the outer ear, the middle ear, and the inner ear. Now, as you can see on the inner ear, it is known as the cochlea, right? Now, it can be modeled as a fluid-filled tube separated into an upper and lower half by a membrane, as shown in figure 11.3. Now, as you can see in figure 11.3, it shows the simplified view of the cochlea and wound to reveal its tabular structure. And it is divided into 5 parts. As you can notice, we have the stapes, the oval window, the basilar membrane, the helicochyma, and the round window. And as you can see on the illustration, at the end of the tube are two windows, right? We have the oval and the round windows on either side of the membrane. Now, the structure of the cochlea is apparent if we imagine a tube folded back on itself and coiled like a shell. The central membrane is known as the basilar membrane, and it ascends along the length of the coiled tube from its base to its apex, where it is perforated by a hole, or the helicochyma. The tube is then tapered, being widest at the helicochyma end. And since the cochlea is sealed, inward movement of the stapes pushes the oval window inwards and causes a column of fluid to move inwards into the cochlea. At the end of the cochlea, the round window moves outwards. Fibers in the basilar membrane run along its length, projecting outwards from the center of the cochlea. And at the base of the cochlea, close to the oval and round windows, these fibers are short and thick. And towards the apex, they become longer and thinner. Sound vibrations in the cochlea, sound vibrations at a particular frequency are transmitted by the stapes and cause motion in the fluid column in the cochlea. This sets up a traveling wave in the cochlea. And at a certain point along the cochlea, the basilar membrane is just the right thickness to resonate at the particular frequency of the cochlear wave. And at this point, along the length of the cochlea, maximum vibratory amplitude will then occur. Now, we will be discussing the next key subtopic, and that would be the sensitivity of the ear. And if we say sensitivity of the ear, under this we have the auditory sensitivity. And if we see auditory sensitivity, it is greatest between 1,000 and 4,000 hertz, the frequency band in which speech is transmitted. And take note, the notes on a piano range from 26 to 4,096 hertz. Now, as you can see in figure 11.4, it shows the sensitivity of the human ear to different audible frequencies. And take note that the sounds below the hatched area are inaudible. Sounds above cause damage to the ear. And as you can notice, the loudness of a noise depends on its frequency as well as its sound's pressure level, or the SPL. Contours of equal loudness have been worked out using large numbers of subjects. A reference tone of 1,000 hertz and say 60 decibels can be presented to subjects. This is followed by a second tone at a higher or lower frequency. And the subject then adjusts the intensity of the second tone until its loudness matches that of the reference. And in this way, contours of equal loudness can be plotted for all frequencies with respect to a series of 1,000 hertz reference tones from 10 to 120 decibels. In order for us to better understand it, let us have an example. So for example, a tone of 100 hertz of intensity, approximately 70 decibels, would sound as loud as a 60 decibels, 1,000 hertz reference tone. And if we say phone, it is the unit of loudness, and it is derived from the equal loudness contour data. In the previous example, so here, in this example, the 70 decibels, 100 hertz tone would have a loudness of 60 phons, okay? And on the other hand, if we see zone, the second loudness measure, and one zone is defined as the loudness of 1,000 hertz tone at 40 decibels. And because loudness perception is a logarithmic rather than a linear process, it can be said that a 10 decibel increase in intensity represents a doubling of loudness. And therefore, a 50 decibel 1000 hertz tone would have a loudness of 2 sounds. And old age is marked by compression of the audible frequency range from 16 to 2000 hertz to 50 to 8000 hertz, a condition known as presbycusis. And the higher frequencies are usually lost first, and most aged people cannot hear sounds above 10,000 hertz, which is why it is better to lower the voice when attempting to communicate with older people. Raising the voice increases the pitch and is self-defeating. The mechanism of hearing loss is at the neural or cochlear rather than the acicula level and is reversible. Now, as you can see on table 11.2, it gives median age-related threshold shifts for men. Now, as you can see, you have there 35 years old. So the threshold shift, that would be 5 decibel. For 45, that's 12 decibels. For 50 years old, that would be 22 decibels. And for 65 years old, that would be 35 decibels. Moving on to our next subtopic, we have noise-induced pathology of the air. Now, take note that sudden noises of sufficient intensity may produce trauma, resulting in a reduction in the efficiency of sound transmission to the cochlea or in cochlear response itself. Now, the tympanic membrane may be ruptured or acicula chain mechanically damaged. This being said, surgical repair may be necessary. Neural hearing loss can also occur, particularly after chronic exposure to loud noises. Now, the largest threshold shifts occur around 4 kilohertz, according to Littman 2000, where the vibration characteristics of the basilar membrane are greatest. The loss is irreversible. And second, in audiometry, such loss is described as a permanent threshold shift. Here, ISO 1999 gives formulae that enable one to predict hearing loss in men and women for different intensities and durations of exposure to noise. Now, as you can see in table 11.3, it gives the median threshold shifts associated with different noise exposures. And as you can notice, the loss at 80 decibels is negligible, but the risk rises rapidly, around 85 to 90 decibels. Exposure to levels as high as 95 decibels pose a serious threat to hearing. Now, audiometric testing determines the minimum intensity or the threshold at which a person can detect sound at a particular frequency. Now, as sensitivity to particular frequencies is lost owing to age or damage, the threshold increases. It is in this sense that hearing loss can be described as a threshold shift. Temporary threshold shifts can occur after exposure to loud noise. Example of this is whenever you want to go visit a club or a clubhouse. Repeated exposure leads to permanent threshold shifts or noise-induced deafness. Now, as you can see in figure 11.5, it shows an example of audiograms of noise-induced threshold shifts. Letter A figure is an example of after 5 years in a noisy job, while letter B figure shows an example of after 20 years in a noisy job. And as you can notice, sensitivity to the higher frequencies is lost first, or the center line gives the patient's average sensitivity. The SPLs are the lowest that the person can hear at a given frequency. Although permanent threshold shifts occur with age, chronic exposure to noise, particularly over 90 dBA, the dBA scale is described in the next portion or slides, hastens their onset and severity. Some airborne chemicals such as toluene have a toxic effect on auditory system and can cause hearing loss, but this is beyond the present scope. On the next key subtopic, we have the tinnitus. And when we say tinnitus, this refers to the ringing in the ears. It is a common auditory effect of exposure to loud noise, both in the short and long term. Now, according to Fon et al. 1993, they actually found that the prevalence of tinnitus was 23% in a sample of 647 noise-exposed workers of average age 39 years, working in industries such as shipbuilding, woodworking, construction, etc. And after controlling for confounding factors such as tympanic membrane abnormalities and ear infections such as otitis media, no significant associations were found between tinnitus and sex, age, race, and exposure duration. However, tinnitus sufferers had significantly higher hearing thresholds at both high and low frequencies, and 30% of them claimed that it interfered with activities such as telephone conversation and sleep. That tinnitus is common in noise-exposed workers and that it interferes with activities of daily living suggests that information about tinnitus and its avoidance should be included in hearing conservation programs. And on the next key subtopic, we have the psychosocial aspect of noise-induced hearing loss. Here, when we say noise-induced hearing loss, it can have serious implications for quality of working life and employability, which is correct because it causes social isolation. It can debar individuals from jobs where teamwork is required, and it can damage promotion prospects as well by lessening the ability to manage others. And therefore, jobs such as sonar operation have precise hearing standards. Now, according to Harris et al. 1979, they found out that high-frequency hearing was essential for a passive sonar listening. Actually, they proposed a hearing threshold level of 35 decibels in the frequency range of 3 to 8 kilohertz, and many people with mild hearing loss would be excluded from this occupation. And the next key area that we're going to be highlighting right now, that would be the measurement of sound. So when we say sound level meters, they provide several different measures of sound intensity. The dB linear scale is actually used to give the sound pressure level, or SPL. This is the root mean square sound pressure at the microphone. Now here, when sound is measured using the dBA scale, a weighting network selectively amplifies or attenuates different frequencies, similar to adjusting the tone control on a modern hi-fi amplifier. The sum of the pressure levels of the various frequencies is called the sound level, or LS. And second, many devices such as electric fans or motors produce intense sound energy at a particular frequency, centered around the 60 Hz mains frequency or harmonics of this. Now, although the sound pressure levels might be high, the weighted sound level is 20 or more decibels lower, since the ear is not very sensitive to sound below 500 Hz. And finally, apart from A scale, some sound level meters have C and D scales. These specialized scales are used to evaluate noise containing intense pure tone components such as noise from jet engines. And on the next key subtopic, we have frequency analysis. And if we say frequency analysis, it is sometimes carried out to obtain further information about the constituent frequencies of a sound source. Octave analysis involves dividing the frequency spectrum into bandwidths, such as the lower boundary, or f sub 1 is 1/2 of the upper, or f2 or f sub 2. So the formula that would be f2 or f sub 2 equals to f sub 1 or f1. The center frequencies of the octave bandwidths are 31.5, 63, 125, 250 Hertz. Further resolution can be obtained by using half or third octave bandwidth, where f2 is equal to the square root of 2f1, which refer to our half octave, and f2 is equal to 3 square root of 2f1, which refer to our third octave. Now, the center frequency of a bandwidth is given by geometric mean of the upper and lower frequencies. Octave analysis and its variations are logarithmic scales and are used to take account of the ear's approximate logarithmic frequency selectivity. They have disadvantages when the goal is to analyze the sound source because resolution drops as frequency increases, such as the bandwidths get wider and all sounds within a bandwidth are added together. Narrowband constant bandwidth analysis may then be used to determine intense sound at a particular frequency. Fortunately, the moving parts of many industrial machines, such as pistons, fans, or gears, are often the primary sources of noise. Since many of these rotate or cycle at known frequencies below 1,000 Hertz, their contribution to the total noise can be determined fairly easily. Now, as you can see in figure 11.6, it shows a third octave analysis of a pneumatic hammer. All right, so the next key subtopic that we're gonna be highlighting right now, that would be several sound sources. Take note that in practice, there are usually several sources of sound, and it is the combined effects of these on the worker that is of interest. The combined SPL from several sound sources can be calculated from first principles, although it is usually estimated by calculating the difference between the two loudest SPLs and adding the amount shown in table 11.4 to the louder of the two. Now, as you can see in table 11.4, if there are more than two sources of noise, the exercise can be continued by taking the combined SPL of the two loudest sounds and comparing this with the third loudest sound. Now, the difference between these is then added onto the estimate of the two loudest sounds to obtain a new estimate of the overall sound. This process can be repeated for each or for other noise sources until the difference between the combined estimate and any remaining sources is 10 decibels, at which point the addition of more noise sources will, in practice, have negligible impact on the overall noise. And the next key subtopic that we're gonna be discussing, that would be measuring noise exposure. And remember, a number of measures have been developed to enable employees' daily noise exposure to be measured. The equivalent A-weighted noise level, or LAEQ, has been developed for those situations where noise levels fluctuate over the course of a day. It is an integrated value, the average level of sound energy over the measuring period. Now, the equivalent A-weighted noise, or LAEQ, is defined as the steady state sound level that would have the equivalent sound energy as the actual noise over the same period of time. The LAEQ can be thought of as smoothing out the peaks and the troughs of the daily noise exposure to give an average. Now, if a worker's exposure times to different noise levels over the course of an 8-hour shift are known, the LAEQ can be calculated as follows. So as you can see, this is the formula of LAEQ, or the equivalent A-weighted noise. And the next key area that we're going to be discussing right now, that would be safe exposure level. Now, as you can see, in the USA, OSHA, or Occupational Safety and Health Administration, has specified 90 dBA as the maximum permissible exposure to continuous noise for an 8-hour shift. Many other countries, including those in the Europe, also regard 90 dBA as the maximum permissible level. However, there is a modern trend worldwide to reduce daily exposures to below 90 dBA. An exposure level of 85 dBA is regarded as the first action level at which workers must be informed and offered ear protection. So the next key area that we're going to be discussing right now, that would be the noise dosimeters. If we say noise dosimeters, this integrates the noise measured at the microphone over a period of time and expresses it as a percentage of the daily allowable noise dose, or as a percentage of 90 dBA for 8 hours. Dosimeters can be used to decide whether workers are being exposed to excessive noise and whether they require ear protection, and also to specify for how long per day they may be exposed to a particular noisy work situations. Now, as you can see on figure 11.7, this is an example of a dosimeter. Equivalent A-weighted noise level and noise dose measurements are particularly useful in hazard surveillance of occupations where the worker is mobile, because they integrate the different intensities of noise, which can vary considerably over the course of the working day. For example, garbage collectors, factory supervisors, and agricultural workers are all exposed to varying noise levels during the course of their work, and an integrated value of their total noise exposure is often more meaningful than isolated measurements made during particular work activity. So this is a clearer and a modern view, or modern examples of noise dosimeters. And the next key subtopic that we're going to be discussing today, that would be integrating sound level meters. Now, to cope with the widely varying types of noise encountered in industry, commercial meters, as shown in figure 11.8, usually have several response modes, normally slow and fast, and sometimes impulse response modes. Now, as you can see in figure 11.8, it is an example of a modern sound level meter with octave filters set attached. The slow mode is used to obtain an average reading when rapid fluctuations in intensity measured on the fast mode are greater than 3 or 4 decibels. In fairly steady noise with fluctuations of only a few decibels, the fast response may be used, and a simple average can be taken by the person carrying out the measurements. And in order for us to understand this, let us have an example. But before that, as you can see on the sample pictures, this is the modern example of what we call sound level meters. Okay, and like I said earlier, let us have an example about this one in order for us to better understand about integrating sound level meters. Now, for example, Fluctuations from 85 to 91 decibels could be interpreted as 88 plus minus 3 decibels. Now, if the fluctuations are greater than 6 decibels, then the average sound level can be estimated as 3 decibels below the maximum value. Having said that, impulse noise cannot be measured accurately with basic meters because their response time is too slow. More sophisticated equipment is now available, and as a rule of thumb, the impact noise level measured with a standard meter should be regarded as an underestimate of at least 5 decibels. And before the measurement of a sound source, the sound level meter should be calibrated. Why? Because meters are commonly sold with a portable calibrator, which itself should be periodically checked. And second, when one is measuring out of doors, it is advisable to attach a spherical windscreen made of foam and of about 5 centimeters in radius over the microphone to prevent wind from distorting the measurements. Now, when operator exposure to noise is being measured, the microphone should be situated close to the operator's ear. And when one is carrying out investigations of the noise produced by machines in offices and factories, supplementary information should be obtained to complement the sound level measurements. And finally, octave, half octave, and third octave sets are available that can be used in conjunction with standard meters. Now, as you can see in table 11.5, these are examples of supplementary information for noise measurements. All right, so the next key subtopic that we're gonna be highlighting now, that would be noise surveys. If we say noise surveys, these are a useful method of evaluating the distribution of noise in a working area and the exposure of workers. Now, occupational hygienists use 2 methods. First, we have the area sampling, and second, we have the personal sampling. For area sampling, the workplace is actually evaluated. This works well if the noise is fairly constant and workplaces are fixed. On the other hand, if people move around at work or if noise levels are closely tied to a worker's activity, personal sampling is necessary. And in some industries, such as construction and mining, a combination of both approaches is best. Now, in area sampling, a plan map of the workplace is actually needed. Sound levels at various locations are recorded directly onto the map, and areas of high and low noise can be identified so that appropriate remedial action can be taken. Noise contours or regions of equal sound level can be superimposed onto the floor plan. In conjunction with the data about the positioning and movement of personnel, a number of steps can be taken to minimize excessive noise exposure, as shown in table 0.6. Now, as you can see in table 11.6, it shows some basic steps in the management of industrial noise exposure, which include short-term measures, medium-term measures, and long-term measures. All right, so the next key area that we're gonna be discussing today, that would be ear protection. And in ear protection, we are normally introduced with earmuffs or earplugs. Now, earmuffs or earplugs, singly or in combination, can protect the ear from excessive noise by providing an airtight acoustic or seal between the atmosphere and auditory canal. Now, in the first picture, so that's an example of earmuffs, and second picture, that's an example of an earplug. Now, if earmuffs or earplugs are used, reductions in SPL at the eardrum of up to 40 decibels are possible. However, for very high noise levels, say about 140 decibels, simple ear protection is inadequate since excessive vibration can be conducted to the cochlea by bone or tissue. Now, as you can see in figure 11.9, it illustrates the effects of ear protection on the attenuation of different frequencies of sound from a pneumatic hammer. And as you can see on table 11.7, it actually gives sample data on the attenuation likely to be achieved using well-fitting, commercially available ear masks. Now, even if ear protection is worn, sound may still find its way into the auditory system, right? Because of this, the protector may vibrate or energy may pass through leaks, usually a problem with homemade earplugs. Some characteristics of effective ear protectors are given in table 11.8. Now, as you can see in table 11.8, it presents the characteristics of an effective ear protector. First, impervious to air. Second, adaptable to shape of the user's head or external auditory canal to form an airtight seal and avoid pressure hotspots to ensure comfort. And finally, remain firmly in place without causing pressure ischemia. Now, size earplugs are reusable and are usually made of soft, flexible materials such as molded plastic. In fact, they come in different sizes and should be cleaned with soap and water after use. In addition, formable earplugs are usually made of materials such as cotton or wax. The user molds the plug into a cone shape to conform to the dimensions of the ear canal. Protection depends on the materials used. Cotton provides the less protection than wax and certain polymers. Earplugs have the advantages of being small and easy to carry, convenient to wear in confined spaces, and cheaper than earmuffs. They are also compatible with long hair or protective headgear. And the main disadvantages, though, are that they take longer to fit than earmuffs and are not always suitable for regular use because the hygiene problems. Unclean hands may transfer dirt to the ear canal via the plug, and earplugs cannot be worn by people with ear infections. All right, so the last key area that we're gonna be discussing now, that would be the design of acoustic environment. Here, we should bear in mind that the alerting quality of noise makes it an ideal warning signal. By the same token, noise can distract workers and is considered to be as a major source of dissatisfaction with the environment, correct? And so for that matter, it is apparent that individuals differ widely in their attitudes to and tolerance of noise. Now, the question is, what are the factors that we should consider then? Well, clearly, many factors need to be considered if an optimal auditory environment is to be designed. Now, according to Woodson, 1981, he has compiled the findings of many studies of the effects of noise on human performance. Although noise levels below 90 dBA are not a serious threat to hearing. In fact, they can degrade task performance and cause annoyance. Now, as you can see in table 11.9, it shows the effects of noise below 85 dBA. Now, for example, you have there 80 dBA, so the effect of noise, that would be conversation difficult. So 75 noise level or 75 dBA noise level, the effect would be telephone conversation difficult, raised voice needed for face-to-face conversation, and so on and so forth. And the next key subtopic that we're gonna be discussing right now, that would be reverberation. Now take note that the noise level in a room depends on the intensity of any noise sources and also on the reverberation characteristics of the room. Now, the sound emanating from a source reaches the listener both directly and after being reflected off the walls and other objects as shown in 11.10. Now, as you can see in figure 11.10, it shows a sample reverberation characteristics of the room. And as you can notice, sound in a room reaches the ear by direct and indirect routes. So if we see reverberation, it is actually the inter-reflection of sound waves inside a room. So the more reflection, then the longer the reverberation time. Now, what I mean about this is that if there is continuous sound, background noise caused by interreflection builds up to a steady level called the reverberant field. Reverberation is a very important acoustic characteristic that influences an occupant's perception of a room as shown in table 11.10. Okay, so as you can see, these are some characteristics of reverberation in rooms. First, reverberation time in a room does not depend on the position of the source or the position of the listener. Second, excessive reverberation is a major cause of the blurring of acoustic signals such as speech. Third, room shape has little effect on reverberation time. And finally, the intensity of reverberant field in a room depends on, first, the sound level of the source, second, the volume of the enclosed space, and finally, the amount of sound absorbing material in a room. All right, I think that's a good place to stop. If you have questions, please let me know on the comment section below. And if you like this video, please don't forget to subscribe and hit the bell button for the latest updates. Thank you.